Hello everybody, welcome to the second part of lecture 7. So today we're covering chapter 4 part 7. Again, chapter 4 is quite long. Okay, so let's see. So today, if I can get, here we go. So this is lecture 7 part 2, section 4.7, and this is Cauchy-Euler equations. Okay, pretty good. All right, let's get another layer here. Okay, all right. I'm gonna lock that layer. All right. So Cauchy-Euler equation. So we have looked at these equations with constant coefficients, homogeneous equations with constant coefficients, and those are pretty roughly easy to solve, right? And then we've looked at how you solve the inhomogeneous version of that, right? So where you have constant coefficients and you have a function on the left-hand side, I'm sorry, right-hand side. Ugh, I can't get my left from my right. We were able to do that in two ways. So one way was the method of undetermined coefficients, which is where we had those restrictions on that right-hand side function. And the other way was variation of parameters, which in theory can work for any function on the right-hand side and can also work when you have non-constant coefficients if you can get the complementary solution somehow, right? Well, today we're actually going to look at a type of equation that has non-constant coefficients that can be solved pretty easily for the complementary solution. Now, in general, when you have non-constant coefficients, so remember, I'll just write down the equation again. I know we've done this a million times, and I think my layer is messed up here. Oh, I locked the wrong one. Okay, unlock. Okay. So we write down this equation. We have, some function of x times the nth derivative of y plus another function of x times the n minus 1th derivative of y plus dot, dot, dot. Again, we've written down this a bunch of times, but just to remind you of the form, times here now, the first derivative plus another function of x times y is equal to g of x on this side, right? Okay. So this is our typical, our most general equation where these are functions of x. Now, in general, for random functions of x on times these derivatives, you need series solutions, and that's what we're going to look at in chapter 6, I believe. So usually you just can't write down a solution. But there's a class of equations called Cauchy-Euler equations in which you can write down a solution, and that's very cool. So these are what we're going to talk about today. So they're Cauchy-Euler equations, and they have a very specific form. And they show up in all kinds of places. Okay, so they look like this, where you have some constant an, and then you have x to the n times the nth derivative of y, plus a constant an minus 1 times xn minus 1 times the n minus 1th derivative of y, and then plus dot, 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 I think you can probably guess, constant a1 times x times the first derivative, plus a constant a0 times, x to the 0, but this would be y, equal g of x. Okay, so this equation, notice that the power of x here has to match the order of the derivative that it's multiplying. Okay, otherwise it's not a Cauchy-Euler equation, and you will not be able to solve for the complementary solution in the manner that we're going to show you in a second. So remember that if you get the complementary solution, which is the solution to this when it's 0, when it's equal to 0 instead of equal to g of x, right? That's all I'm going to write. Well, I should have written it a different way, but equals 0, that's homogeneous, right? and of course non-homogeneous here, but when you get the complementary solution to the homogeneous equation, if you have a way of getting that, and you will for Cauchy-Euler equations, then you can use variation of parameters to get your particular solution like we showed last time. Okay, but it's very cool that in this type of equation you can actually solve for the complementary solution without some crazy series solutions, which we are going to learn about. I like series solutions, they're fun, but you know, a lot of work. Okay, so let's see. So how do you solve for this? Well, you can try y equals x to the m, where m is something you got to solve for. So let's just look at a second order equation, and it's nice to start there. So let's look at a second order Cauchy-Euler equation. And I'm going to write it out like this. Just write it all out. Plus bx times dy dx plus cy. And we're going to look at the homogeneous version and show you how to solve using this. Okay, so we're going to substitute this in. So let's see, y prime is equal to mx to the m minus 1, and y double prime is equal to m times m minus 1 x to the m minus 2. And now, well, notice when we substitute this in, what's going to happen. So let's substitute it in. We have a times x squared, then we have m times m minus 1 x to the m minus 2, then plus b times x times m times x to the m minus 1, that's that first derivative, and then plus c x to the m equals 0, right? Now notice that here the x squared times the x to the m minus 2 just gives me back x to the m. The x times the x to the m minus 1 gives me x to the m, and I have x to the m here, and I'm going to end up with a polynomial equation in m, which is great. So this is why the Cauchy-Euler equation can be solved, and this is why the powers have to match. So the power of x here has to be the same as the number of derivatives you're taking on, that you're multiplying by, okay? All right, so let's do that. Let's just write this as a m minus 1, and then we have this is going to be x to the m plus b x, bm mx to the m plus cx to the m equals 0. And that means I can just get rid of these and I get this polynomial equation. And I'm going to write it out. am squared minus am plus bm plus c equals 0. And just writing it in the sort of standard form for a quadratic equation. am squared plus b minus am plus c equals 0. And of course you can solve for m. And then you know what your solution is. And you will get two roots, of course, right? Two roots. Solve for two roots, two values of m, two values of m, m1 and m2. And then your complementary solution, of course, is a constant times x to the m1 plus a constant 2 times x to the m2, okay? So this is a really nice technique. Now, just like we had when we were learning to solve these equations, these type of equations with constant coefficients, right, the homogeneous version, we had to look at the different cases, right, what the different cases were for these roots. And that's what we're going to do now. Okay, so we have three cases. So we have one, the first case is distinct roots. Okay, so distinct roots, this is of course m1 not equal to m2. Then things are super easy. That's the case we kind of had down here, right? And I should say this, that I wrote this down, but really I should say this is only when you have distinct roots, because we got to do other things. So I'll put a little star here. Only for distinct real roots, in fact. Okay, so I got a caveat there. All right. When this is the case, then that is actually true, right? Then we get our complementary solution is just c1 x to the m1 plus c2 x to the m2, okay? All right, so for the second case, and that is repeated real roots, so this is when you have two roots that are the same. And again, you know, if you want to know which of these cases you are going to be in, you're going to check your, you know, b squared minus 4ac, and just be careful that this here, right, this is the coefficient of m, so this is our b, right, and it's bad to use the same notation here, but this is what you would, this whole thing is what you would stick in the quadratic equation. I think you guys know that, but just be careful. Okay, so you would check that to figure this out. In this case, you know, you have m1 equal to m2, right? So in that case, you certainly can have y1 is equal to x to the m1, but then you have to get a second linearly independent solution, and we know how to do that. Note that m1 is going to be, you know, minus b over 2a, right? So it's minus b minus a over 2a, right? So that's what m1 is. And now we need to get that second linearly independent solution. So let's just, again, we're only dealing with second order right this second. So if you do a second order, if we want to write this second order equation in the standard form so that I can move forward with finding my second linearly independent solution, then I'm going to rewrite my equation. So here's my equation, right here, right? I'm going to rewrite it in standard form. So I need that d squared y dx squared by itself. Okay, plus I'm going to have b over ax, right, because one of the x's canceled, dy dx plus c over ax squared y equals 0. Okay, so right here is that p of x function that we always are using for when we're finding that second linearly independent solution. And just to remind you, you want to go back in your notes or in your book, that y2, the second solution we're looking for, is y1 times the integral of e to the minus integral p of x dx over y1 squared dx. Remember that? Okay. And so let's substitute in. First, actually, I think I want to do that integral by itself first. So I'm going to do this little integral, kind of come over here, do my integral of p of x dx. That's the integral b, well, put b over a outside, 1 over x dx. So it's b over a ln of x. And then when if I take e to the minus integral p of x dx, what do I get? I get e to the b over a minus b over a ln of x, and I can pull this up on an exponent up here onto the x, so that I get just x to the minus b over a. Okay. All right. So that becomes what this whole thing here is, right? So I'm now going to substitute on. I have y1, which is x to the m1, and then I have the integral of x to the minus b over a, and then over x to the m1, and then dx. But remember what m1 is, so I'm going to put that in. So we have x to the m1. I'm going to leave it off here because it's just, you know, more work, because I don't have to integrate that. We have x to the minus b over a. And then on the bottom, we have x to the minus b minus a over 2a. And it's squared. Oh, sorry, this should have been squared. 2m1, right? Because it's squared. Sorry about that. Squared, so there's a 2 here. And so when we come down here, we have x to the m1. And then we have the integral of x to the minus b over a. And then this is the minus, so I can bring it up here, and the 2's cancel, by the way, right? And so I get times x to the b minus a over a. So notice when we add these two exponents that this minus b over a will cancel with this b over a, and then I'll just get minus a over a, right? So, and this is dx, of course. So we got x to the m1, and then I have x to the minus a over a, which is minus 1, so I get 1 over x dx. And so I get x to the m1 ln of x. Okay, so here is the solution for our second. Again, I could put in what m1 is, but I'm just not. Here's our solution for the second linearly independent solution, right? So that's y2. So that means that yc is going to be some constant times x to the m1 plus the second solution times a constant x to the m1 ln of x. Okay, so that's the case when we have 2, and you know what m1 is. It's that minus b minus a over 2a. That's the case when we have 2 repeated roots. Okay, well, as you know, there's a third case, and that is when we have complex roots. So let's look at that case, case 3. Complex conjugate roots. So remember, you know, if you have this equation, right, so let's write it down again. I'll write it down up here, right? So we have the equation for m that we had, and where did I put it? Let's see. There we go. So we have am squared plus b minus am plus c equals 0. Okay, so when we have that, we of course use the quadratic equation to solve it, and we might end up with b squared. Remember, this here is our quote-unquote b for the quadratic equations, you know, as far as the quadratic equation is concerned. And so we might end up with a negative under the square root, and we'll get complex conjugate. Now, so we used to write, for the previous case where we had constant coefficients and we were solving for the complex roots again, we wrote this as m1 equals alpha plus I beta, remember that? And m2 equals alpha minus I beta. And go back and remind yourself what those are. But beta is real, okay? All right, so the solution in that case, right, is our y equals, I'm sorry about the lawnmower, by the way. Fun times, okay. Hopefully you can hear me. So is x to the alpha plus I beta, right? Plus c2 x to the alpha minus I beta. All right. So when the so we can actually manipulate this a little easier, and it's kind of an interesting thing. So let's take a look at this. If you have x to the I beta, right? Because this is x to the alpha times x to the minus I beta, etc., or x to the alpha times x to the plus I beta, right? So if you just have x to the I beta, well, I can write that, and this is a cool trick, as e to the ln of x to the I beta, right? Can't I? Because e to the ln x is just x, and then the whole thing is to the I beta. So that's very cool, because I can write now that as e to the ln to the I beta ln of x, right? So that's really a nice thing. So because what we can do now is we can write things in terms of sines and cosines, right? So if I come down here again, I have x to the I beta, and I can write that as, of course, e to the I beta ln of x, and I can write that as cosine of beta ln of x plus I sine of beta ln of x, right? So because this, of course, is e to the I beta ln of x, so this is just the Euler formula, and x to the minus I beta is e to the minus I beta ln of x, so that is just cosine of beta ln of x minus I sine of beta ln of x, right? So very cool, which means we can do what we did before when we were looking at constant coefficients and change everything to sines and cosines. Okay, so notice that x to the I beta plus x to the minus I beta is equal to 2 times the cosine of beta ln of x, and x to the I beta minus x to the minus I beta is equal to 2I times the sine of beta ln of x. All right, so we can see that if we choose the right constants up here, right, that we can write everything down in terms of sines and cosines. So for instance, I can write y1, right, is equal to x to the alpha, x to the I beta, plus x to the minus I beta, right? And that's just because what I'm doing is choosing different constants instead of and writing it this way. Okay, and then I can write y2 as equal to x to the alpha, x to the I beta. Now we didn't go through all this last time, but I'm showing it to you this time. Okay, and so this y1 would be just 2x to the alpha cosine of beta ln of x, and this y2 would be, I think I said y2, I mean y1 would be that, would be just 2I x to the alpha sine of beta ln of x. And so now, again, I didn't show all this math last time, but it was really the same thing. So now I can just absorb the 2 and the 2I into the constants, and I can write my full complementary solution as x to the alpha times c1 cosine of beta ln of x, and then plus c2 sine of beta ln of x, right? So this is very similar to what we had for the constant coefficient case, except for we don't have this ln of x in there, right? We just had like beta x. All right, so remember what beta was. So alpha is minus b minus a over 2a, and beta is b squared. So it's our b, which is b minus a squared minus, this is not right because I've got to change the sign. So it needs to be no negative sign under the radical. Okay. All right. We got rid of that. We pulled the I out. Okay. So it's the square root of 4ac minus b minus a squared. Okay, remember that's what beta is. Okay, so we've gone through the 3 cases. Let's actually do some examples of the cases. Okay, for specific equations. All right, let's go back to examples. Oh, I need a layer. Hold on, I messed up here. Definitely messed up. All right. Okay. So let's look at the equation x squared d squared y dx squared minus 2x dy dx minus 4y equals 0. This is definitely Cauchy-Euler because look, it has a 2 and a 2, a 1 and a 1, right? 0, 0, right? So the powers of x match the derivative. So it's Cauchy-Euler, good. So we can substitute y equals x to the m in there. So y prime is m, x to the m minus 1. Y double prime, second derivative, is m minus 1, x to the m minus 1. Oh, sorry, minus 2. Sorry about that. And now we substitute in, we get x squared, m minus 1, and then x to the m minus 1. Oh, sorry, 2. Minus 2x m, x to the m minus 1, and then minus 4x to the m equals 0. And here you can see this is going to combine to give me x to the m. So I get m minus 1, x to the m minus 2, and this is going to combine to give me x to the m, x to the m minus 4 x to the m equals 0. And I can cancel these out, and I get my equation that tells me about m. So m squared minus m minus 2m minus 4 equals 0. Let's see, did I do that right? Minus m minus 2, right? Yes, okay. So this is m squared minus 3m minus 4 equals 0. Let's check out what the case is. So I'm going to check my b squared minus 4a. So b, 4ac, I mean, okay. B squared minus 4ac is equal to b squared. This is our b, right? So we have 9 minus 4 times 4. Okay, hold on a second. So, right, so this is minus 4 times a, which is 1, times another minus 4, right? So we're going to get a plus. Okay. So we get 9 plus 16, which is 25. Okay, cool. So now we're going to have distinct roots, right? Because this is real. And remember what m is, right? M is going to be minus b, so minus b, which is this, so it's 9 over 2a, and a is 1, plus or minus the square root of 25, which is 5 over 2a, right? So what does that give us? I did it again. I'm always doing this. I always either make it 2 times b or not. So this is b, not b squared. Okay, so 3 over 2. Sorry about that. Okay, so if we use the plus sign, right, we're going to get 8 over 2, so we're going to get 4. And if we use the minus sign, we get minus 2 over 2, so minus 1. So we have our 2 distinct real roots for m, which is good. And that makes our life super easy because I can just write down the complementary solution, right? It's c1 x to the 4 plus c2 x to the minus 1. There you go. Nice. So these Cauchy-Euler equations are awesome because they are easily solved, right? Okay, so let's look at the next case. And we'll try to see if we can do it down here. So we get 4x squared d squared y dx squared plus 8x dy dx plus y equals 0. Okay. So let's put in our x to the m, right? Our y equals x to the m is our guess. Again, the derivatives are up here, so I'm just going to use those. Okay. So we have 4x squared m minus 1 x to the m minus 2 plus 8x m x to the m minus 1 plus x to the m equals 0. And just going to quickly combine these. You can see that the powers are going to, this is always going to happen on a Cauchy-Euler equation. And we're going to get x to the m on every term, and we can cancel that. So I'm just going to not do that step. we get m minus 1 plus 8m plus 1 is equal to 0. Okay. Now, here, let's combine. So we have 4m squared minus 4m plus 8m plus 1 equals 0, which gives me 4m squared plus 4m plus 1 equals 0. All right, let's check our b squared minus 4a. Okay, this is, of course, b, 4ac. Why can I not say that right ever? B squared minus 4ac. Okay, so b squared is 4 squared, which is 16, minus 4 times a, which is 4, times c, which is 1, right? So, well, there you go. It's 0. Okay, so remember m from the quadratic equation is b, which is 4, I'm going to do this right this time, over 2a, which is 2 times 4, right? Plus or minus 0, right? So these are the same roots, and they're all equal. I mean, they're two roots that are equal, right? So we get 1/2, and that is the root of this. Oh, sorry, the minus, right? Because it's minus b over 2a. So we have minus 1/2. Okay, good. But they're the same, right? There's two roots that are exactly the same, right? Minus 1/2 plus 0 and minus 1/2 minus 0. Okay, so we have to use our ln of x solution. We don't have to go through all that math again because we know exactly what the second linearly independent solution is, right? So we can just write this down. YC is c1 x to the minus 1/2. That doesn't look like a 2. There we go. Plus c2 x to the minus 1/2 times ln of x, and there it is. Okay, so super nice. Okay, all right, not too bad. Okay, you just got to recognize what case you're in. Now, what if you have a higher order equation? So right now we're just dealing with second order equations, but what if you had a higher order equation and maybe it might have like 3 roots that are exactly the same, right? We had this situation also with the constant coefficient solutions, right? Well, in this case, what would you do? Well, you'd have the first one would be x to the m. So let's say m1 has, 5 roots. There's 5 roots equal to m1. Well, the first solution would be x to the m1. The next one would be, of course, x to the m1 ln of x. The third one, you would write x to the m1 ln of x squared. The fourth one, you'd write x to the m1 ln of x cubed. And one more, x to the m1 ln of x to the 4th. And of course, if you had more, you just keep going up in powers of ln of x. So it's pretty simple when you have even, 10 roots that are the same, right, in some much higher order equation. All right. All right, one more example, I think. If I can get my pages right. Okay. All right, let's go to a new layer for that. All right, so we're going to look at an initial value problem. All right, so we're going to have 4x squared y double prime plus 17y equals 0. Okay, and look at this. It doesn't have a first derivative term. Fine, it's not a problem, right? You can have any combination. You don't have to have all of the derivatives in a Cauchy-Euler equation. The only thing you have to have is that the power of x has to match the number, the order of the derivative, right? So that's the only thing you have to have. And we have that here. We have x squared in a double prime, and we have x to the 0, right there, which is 1, times y. You don't have to have all those other terms. And in this case, you're missing one term, right? Okay. And let's look at the initial value where y1 is equal to minus 1 and y prime of 1 is equal to minus 1/2. So it's y at 1 is minus 1, and y prime at 1 is minus 1/2. So this is initial value. Okay, first of all, it's Cauchy-Euler. Let's say solve it. So y equals x to the m. And I'm just going to write down the derivatives just for reference. Okay. Okay, perfect. Now we're going to put that in. So 4x squared times m minus 1, x to the m minus 2 plus 17x to the m, right? Because we don't have that first derivative term. And this, of course, is going to combine to give me x to the m, and this is already x to the m, so I'm just going to cancel that out. So we get 4m minus 1, right, plus 17 equals 0. And this becomes 4m squared minus 4m plus 17 equals 0. And again, we have a quadratic form. Okay, let's check our b squared minus 4a. And you can 4ac. I don't know what's wrong with my brain. Okay, so I think you can probably guess that we're going to have a negative, right? So look at b squared minus 4ac. Okay, so b squared, here's b, is 16, and then we have 4 times 17, right? So that is, sorry, it's 4 times a, which is 4, so I'll put that over here, times c, which is 17. So this is certainly going to be negative. Okay, so this is actually 256, luckily. Okay. All right, so, sorry, minus 256. So what we're going to do is we're going to do that thing we did before. We're going to pull the negative sign out and put an I here and just make this 4ac minus b squared, which of course is just going to be I times the square root of 256, which I hope you know is perfect square of 16. Perfect square of 16. All right, and so now what are our m's? So m is equal to minus b. So minus b is minus of a minus 4, so we get 4 over 2 times 4, right, because a is 4. And then plus or minus I times 16 over 2 times 4. So we get 1/2, and it is a positive 1/2, right, because there's no minus signs here. And then plus or minus I over, this is 8, 16 times 2. So that big ugly thing ended up being pretty nice. And these are our m's, and they're complex conjugate, right? So they're 1/2 plus 2i and 1/2 minus 2i. Okay, complex conjugate roots, which is always the case when you have a situation like this. Okay, so we already know how to write down the answer for this, right? We're going to use the cosine thing. We don't have to go through all the math, right? And again, when you're working on a problem or on a test in this class, you do not have to memorize this stuff. Go look, it's open book. Go look in your book for the form of the equation. And so our form is x to the alpha, which is 1/2, right? So this is alpha. And this 2 is a beta. Okay, and then we have C1 cosine of 2, which is beta, ln of x, plus C2 sine of 2 ln of x, right? And that's our solution. And now we need to apply our initial conditions here. So here we have y of 1 is equal to 1. Okay, so let's try that. So we're going to say y at 1 has to be, minus 1. It's minus 1. And so we're going to put 1 in for x. So we have 1 to the 1/2, which is just 1. And then we have C1 cosine of ln of 1, which is 0. So that's just going to be 1. So cosine of 0. Plus C2 sine of 0, which is 0. and we just get 1. Sorry, so, no, stupid, sorry. C1, right, because this is 1, this is 1, so I just get C1. So that tells me C1 is minus 1. Okay, all right, great. Let's do the next thing. Let's take the derivative. Okay, so first we have to take the derivative of this function, and, you know, it's kind of a pain to take that derivative. All right, so we've got to bite the bullet and actually do the derivative. Fun times. Okay, so it's kind of a pain, but we can do it. It's got caught in all my papers over here. Okay. All right, so let's do y prime. So, and then we'll stick in our 1, right? So first of all, everywhere there's C1, we can put a minus 1. But I'm going to do that when I'm done with the derivative. Okay. Byproduct rule. Take the derivative of this part first. I get 1/2 x to the minus 1/2 times C1 cosine of 2 ln of x plus C2 sine of 2 ln of x. Okay, then the second term, I got to take the derivative of all this. All right, so it's plus x to the 1/2, and then we have the by chain rule, right? That we've got to take the derivative of the cosine and then multiply it by the derivative of what's inside. Okay, so the derivative of cosine, of course, is minus sine. So I'm going to put minus C1 sine of 2 ln of x, and then the derivative of the inside is just 2 over x. So 2 over x. And then the derivative of sine is cosine plus C2 cosine of 2 ln of x. The derivative of the inside is just 2 over x. Okay, phew. All right. Now I'm going to do what y at 1 is, y prime at 1. Well, that makes that just 1, so I just get 1/2. And then over here, this is 0 because ln of 1 is 0 and sine of 0 is 0. And here, this is minus 1, C1, and this is cosine of 0 is 1. And so what I'm going to get is just a minus 1 here, because that's the C1 part, right? And then the next term over here, x to the 1/2, when x is 1, is just 1. This is going to be 0 because the ln of x is 0, and you get sine of 0 is 0. And I'm going to get a term here that's just C2 times the cosine of 0, which is 1, times 2. So I'll just put the 2 over here because x is 1, right? Okay, and this needs to be minus 1/2. Well, I hope you can see that immediately that this means that C2 has to be 0. Solve it if you like. All right, so now we have our two values, and we can actually write down the solution. So y is x to the 1/2, and then C1, which is minus 1, minus cosine of 2 ln of x. And the C2 is 0, so that's our answer, right? And I could write it nicer, so minus x to the 1/2 cosine of 2 ln of x. There we go. All right, so those are our three cases. So we're not really going to deal with higher order. You can, if you like, go look at that, but really all it entails is using these same rules, right? You're putting in your x to the m as a solution, and solving a higher order polynomial, right, which is always a pain. And dealing with if you have a couple of complex conjugate roots, deal with them like this. If you have a bunch of repeated roots, deal with them the way that we just did in the previous example. And your distinct roots are fine, right? But it's really not much more complicated to go higher order, except for you have to solve a higher order polynomial, right? And that's kind of, like I said, a pain. All right, so that's the end of Cauchy-Euler equations 4.7.